Here's a somewhat complex circuit that shows a combination of two resistors and a capacitor along with a battery. This is something we haven't seen yet in any of the video lessons for this unit 3.2. My advice for you when you encounter problems like this is to think of the capacitor as having an effective resistance to it. An effective resistance. So in the previous lesson, I referred to initial condition versus steady state values. So all we mean by initial condition is maybe like immediately after a switch is closed or immediately after the circuit is connected, something like this. Now in the example provided here, there is a switch in the circuit. So we might say, in fact, I think we should go ahead and read what the problem suggests here. In the circuit shown above, the switch is initially open and the capacitor is initially uncharged. Okay, so there's our initial condition, no charge on the capacitor. In that initial condition, a capacitor has an effective resistance of 0. In other words, an uncharged capacitor behaves like a resistor of 0 resistance. It behaves like a perfect conductor. Although in time, we know capacitors gradually reach the maximum charge they can achieve, and at that point, no more current flows to a resistor. There's no more attempt to charge it, and so the effective resistance of a fully charged capacitor is infinite. Right, so in the initial condition, the, what do we call this? REFF, the effective resistance of the capacitor is equal to 0, and in the steady state, the effective resistance of the capacitor is infinite. If you keep that in mind, then you can actually solve what appear to be complex circuits in a fairly simple way. So let's use this as an example of applying this idea that a capacitor behaves like a resistor of 0 resistance in the initial condition and infinite resistance in the steady state. Our switch is closed, and a graph of the voltage across the capacitor, so I guess there was a voltmeter placed here in the circuit. Yeah, a graph of that capacitor voltage versus time is shown. So we see that that voltmeter in the steady state, meaning after a long amount of time, we can tell that 12 represents an asymptote. That's the maximum voltage across the capacitor. Here are the questions we have. First of all, determine the amount of voltage across the resistor R2 immediately after the switch is closed. Then determine the voltage across that same resistor in the steady state a long time after the switch is closed. The value of that resistor isn't given in the problem. So that's the third question we have. Calculate what the value of that resistance happens to be, and then finally calculate how much energy is stored in the capacitor after a long time. So we keep hearing this phrase, after a long time. We can translate that as steady state. If we see a phrase like immediately after the switch is closed, translation is initial condition. Actually, the problem doesn't end here. There's a part E, but we'll get to that. Okay, so back to just our conceptual level understanding of how a circuit like this behaves. Identify the junctions. When the switch is first closed, there's going to be some current flowing through the battery. Whatever the current through the battery is the same current that flows through R2, and then that current reaches a junction. Now, it's going to split up. I guess some of the current could take the path between junctions A and B by flowing through 15,000 ohms of resistance, or in the initial condition, the current could take this second path. So we'll call this maybe I total, I subscript TOT, I total. And then we'll call this I1 and I2. Now you know by Kirchhoff's junction rule that I1 plus I2 has to equal this I total. Let's think about the ratio of these currents, I1 and I2. Remember, in the initial condition, the capacitor behaves as if it's a resistor of zero resistance. So at the very instant the switch is closed, the value of I1 is actually 0. None of the current would flow through a path that has 15,000 ohms of resistance when there's a path that's available that has 0 resistance to it. So what I'm about to say isn't true indefinitely, but in the initial condition, right when the switch is first closed, the current just takes this outer loop, and there's no current at all flowing down this branch of the circuit. And so we could imagine, what if we took 2 voltmeters, 1 voltmeter connected across the resistor and another voltmeter connected across the capacitor? Well, we already know initially what the voltage across that capacitor is. It's given for us here, right? That's 0. Well, then by Kirchhoff's loop rule, not the junction rule, by the loop rule, the voltage gained by the battery of 20 has to equal the voltage lost across the resistor plus the voltage lost across the capacitor. But the voltage lost across the capacitor initially at time t equals 0 is 0. So the voltage across the resistor initially is the full 20 volts. It's a long way to get to our answer to part A, but that answer is grounded at a conceptual level. So 20 volts. Now, what's the reading across that voltmeter in the steady state a long time after the switch has been closed? Well, now that comment about the way in which current breaks up past the junction labeled as junction A changes, all right? Some current flows through the battery. It flows through resistor number 2. It reaches the junction at point A, and now some of it actually will flow through the resistor R1, and some of it flows to the capacitor. I shouldn't really say it flows through the capacitor because that's a insulator. Okay, so in what ratio do these currents that I might label as I1 and I2 split up? Well, now in the steady state, how does the capacitor behave? As if it has an infinite number of ohms of resistance. And so in fact, I2 would be equal to 0. And so in the steady state, the circuit behaves such that this loop on the left, the current that flows through the battery and through R2 and through R1 is just one single current, and there's 0 current flowing on this branch of the circuit here. So how could we determine what the voltage across resistor number 2 is? Well, resistor number 1 is in parallel with the capacitor. Whether I go from point junction A to junction B across resistor 1, or I go from junction A to junction B across the capacitor, it still represents a potential difference between points A and B. And in the steady state, we know that the voltage across the capacitor is 12 volts, which means in the steady state, the voltage across resistor number 1 is 12 volts. In other words, if we take our 2 voltmeters and connect them across the 2 resistors, And we know in the steady state, this voltmeter reads 12 volts because it's in parallel with the capacitor, which reads 12 volts in the steady state. And so by Kirchhoff's loop rule, this one has to read 8 volts, so that the two voltages across the resistors add up to equal the voltage of the battery. So there we have it, 8 volts. So what's the value of this resistor number 2? Well, let's see. The voltage across resistor number 1 compared to the voltage across resistor number 2 as a ratio is in the ratio of 8 to 12. Or what's that, in the ratio of 2 to 3? Well, it turns out, if you remember from our study of voltage dividers earlier in this lesson, the ratio of the voltages in a voltage divider is equal to the ratio of the resistance. So the resistance ratio has to be 2 to 3. Resistor number 1 is, well, boy, they sure chose some non-intuitive values for the subscripts. Seems more sense to me to refer to this as resistor number 1, and this one is resistor number 2. Anyway, so how about this? Just to make sure we're consistent with the terminology, I need to refer to this as V2 because this is already labeled as R2, and refer to this as V1. So in any case then now, V1 over V2 is equal to 12 over 8, right? This is the voltmeter V1 that reads 12 volts in the steady state. So by Kirchhoff's loop rule, V2 in the steady state, in other words, after a long time, has to read 8 volts. That's also the ratio of R1 over R2, consistent with how they're labeled here. Now, R1 is 15 kiloohms, R2 is the quantity we're trying to solve for. So we can say 15 over X is equal to 12 over 8. So if we cross multiply, X is equal to 8/12 of 15, or in other words, it's equal to 2/3 of 15, or in other words, it's equal to 10 kiloohms. All right. Calculate the amount of energy stored in the capacitor a long time after the switch is closed. Well, energy in a capacitor is either 1/2 CV, 1/2 CV squared, 1/2 QV, or Q squared over 2C. Now, which one of these is makes the most sense? We haven't determined the amount of charge on the capacitor in the steady state or after a long time. So any of the equations that has Q isn't really helpful. I think 1/2 CV squared is the way to go. Now, don't make the common mistake. Don't be average. Be better than that. The average student might say, piece of cake, 1/2 times the capacitance, which was given for us, 20 microfarads. Easy, easy. That means 20 times 10 to the -6 farads, and then times voltage squared. And the voltage was given to us. It's 20 volts. No. That's the voltage across the whole circuit from point X to point, well, I was going to call it Y, but I think we've already given a name to that point. We've been calling that point B, right? Anyway, the voltage across the capacitor is VAC. It's not V I'm sorry, VAB. It's not VXB, so it's not 20 volts. What is it? Well, it's 12 volts. Yeah. Okay. Oh, you didn't need me to tell you that. You weren't going to make that mistake. I know it. Grab a calculator. Let's see what we get. So we can call this 1,440 microjoules, or we can call it 1.44 millijoules. We can call it 1.44 times 10 to the negative third joules, whichever you prefer. I kind of like 1.44 millijoules myself. So now we've got a graph of the current in resistor number 2. Which one is resistor number 2? Yeah, this one, the one that was initially unknown, but now we know it happens to be 10 kiloohms. We have to make the graph of the current through that resistor as a function of time from 0 to 15 seconds. Okay. Well, let's see. Initially, right when the switch is closed, the amount of current in the circuit depends on this initial condition that says none of the current is going to flow through this branch between points A and B if an uncharged capacitor has an effective resistance of 0, then the current that reaches this junction doesn't really split up into two paths. It all takes the path to the capacitor. So the initial value of the current at time t equals 0, we'll call this I naught, should be equal to the 20 volts provided by the battery divided by just the resistance of R number 2. So 20 volts divided by 10 kiloohms, well, 20 divided by 10 would give us 2, but because we're dividing by kilo, I guess that means 2 milliamps is the initial value. Okay, now let's just jump to the steady state. Call this I subscript S. In the steady state, again, there's 20 volts across the total circuit, but then in the steady state, this is no longer the branch in which current doesn't flow. Instead, the current that gets to this junction would all go through the path, including both resistors, and this represents the branch on which no current is flowing. So it's as if we just have these two resistors connected in series, which would have an equivalent resistance of 25 kiloohms. So if we divide 20 volts by 25 kiloohms, well, 20 over 25 is the same thing as 4/5. That would be 0.8 amps, but we're dividing by kilo, so I guess I mean 0.8 milliamps. Okay, so we need to pick some sort of scale on here. How about we choose every one of these major lines represents about 0.5. So 0.1, 0.2, 0.3, 0.4, 0.5, 6, 7, 8. Okay, so that's where 0.8 milliamps, we're graphing current in units of milliamps. And then this, of course, would be 2 milliamps. So let's fill in an asymptote here. That red line represents the asymptote for the steady state, and then this value of 2 milliamps represents the initial condition for current across that resistor number 2. So how do I know how much curvature to put into this graph? Well, it looks like from nearly 5 seconds onward, we're almost in the steady state at 5 seconds, right? So same thing here. After 5 seconds have gone by, we're nearly down to our steady state values, so that's probably a pretty good graph for the current versus through resistor number 2 as a function of time. Last question, part F, this is a long one. Resistor number 2 is removed and replaced with a lesser resistance. So we've still got our 20 volt power supply. We've still got this 15,000 ohm resistor. Still have the same capacitor, but the resistor in this place is now something less than 10. Okay, well, that means in the steady state condition, right, we know initially all the current is going to choose this path. Choose might not be the right expression, right? Current is not sentient, but in any case, you get what I'm saying. In the steady state, then all the current chooses this path. So if the resistance here is less, then the way in which these two resistors create a voltage divider changes, and an even greater fraction of the 20 volts would be measured across points A and B, right? So in our first example, in the steady state, it's 8 volts across this resistor and 12 volts across this resistor. But by making this less resistance, then this would be something less than 8 volts, and this would be something greater than 12 volts. And so the energy in the capacitor we said is 1/2 CV squared, but since this value of V is increasing, then that means the energy in the capacitor would be greater. So I think we've explained the reasoning well enough, and that concludes this lesson. Thanks for watching.